Okay, well, it's a pleasure to be here. Okay, so the goal of the first two lectures is to introduce the Seiberg-Witten equations and start doing stuff. So, so there's a lot of differential geometries, particularly the dimension 4. I'm going to mention a bit of it, but the first thing is self-duality and self-duality. So, I've got a Riemannian four manifold. It's oriented. So once it's oriented, it has a preferred volume form. In terms of the fact that if E1 through E4 are both oriented orthogonal basis, then this is a preferred volume form independent of the basis. And it implies the existence of the Hodge-Star operator. Hodge-Star operator is sort of a differential geometric implementation of or reflection of quantity duality. And the Hodge-Star operator changes a K form to a 1 minus K form. And it has it's characterized by the fact that if you have a K form, then eta wedge star operator that is the length of eta squared times the volume. And in dimension 4, it has a property that star squared is tells you the parity of the form of the flatter even. In particular, the Hodge-Star restricted to two forms. Its square is 1. So the two forms decomposed into the plus and minus 1 eigenspaces. So, by the way, that's my notation for two forms on our format for X. Okay. Sometimes the X will appear and sometimes not. Actually, in fact, to save space, I'm going to just write the plus and then the minus for these guys. So concretely, basis, I think that if I take only the normal basis, then a basis for lambda plus local frame for lambda plus. Is like that, but I keep E1 fixed and then I cyclically permute the remaining guys. And if I want lambda minus, if I want lambda minus, then I just stick a minus sign here. Right? You notice a couple of interesting things that are very important to notice. So these guys have the interesting property that, well, if omega plus or minus, or omega plus or minus, then omega plus wedge. Well, actually, let's just start off with plus and then minus later. The wedge product of this guy with itself, with this definition, well, this guy's it's much stars itself. So these guys don't square root of lambda plus the volume form. If instead I put in a minus sign, then I get negative the length squared times the volume. So that's one useful fact. And another useful fact is that pointwise, pointwise, the wedge product of self-dual and then anti-self-dual form is 0. Okay, so you can check that on this basis. Those are important algebraic details. So in particular, wedge omega is equal to length omega plus length is plus part minus the length square root of minus plus times the volume. So another important fact is that the star forms is formally invariant. Indeed, if I replace the method by a formal change, then the high star, if this is P prime, then a high star of P prime and lambda k is e to 4 minus that's the 5 star for G. This is the thing from the K. Sorry. 2K. So in particular, if K is 2, it's independent. Okay. And so another couple of things to notice. So the dimension of lambda 2 is 6, of course. And what you're seeing here is that lambda 2 has a quadratic form on the wedge product. It's a symmetric form. And what you're seeing is that that symmetric form is its signature is 3, the self-dual part is the positive subspace, the anti-self-dual part is the negative subspace, and they are orthogonal. So, okay. Now, this is pointwise story, and then then theory. Oriented manifold, then the Dirac homology of X is isomorphic to the harmonic forms. So that's omega k of x, so that say x is closed. At the moment, x is closed with no boundaries. The harmonic form means it's Laplacian and 0. That's the same. That's saying that if your derivative is 0, the adjunct of the exterior derivative is 0. It's isomorphic, but under this isomorphism, H2, yeah, yeah. So the harmonic two forms decomposed into harmonic self-dual and harmonic anti-self-dual forms. This guy is equal to the omega, say Laplacian omega 0, and sorry, omega. Well, this is where they're anti-self-dual. So of course, and this is a reflection of the fact that we already saw the so in Andresh's lecture, he introduced the intersection form of the two-dimensional cohomology, and it passes after tension with the reals to quadratic form here. And the isomorphism between singular cohomology and ground cohomology. So it's the cut product of the wedge product. How many people have actually proved that in their lives? And this decomposition reflects the kind of signature in differential geometric terms. So A plus is maximal positive definite subspace. So, let's see, for the intersection point UX. And you notice it's positive because, as we noted here, when I wedge together the wedge product, it's the cup product. When I wedge together the functional form, it gives me something positive. Right. So when we integral omega wedge omega over x, integrating that equality over there, it's equal to the integral. So it's introducing my notation for the L2 norm. This equation, so that explains why this is a maximal positive definite subspace. Similarly, H minus is a maximal negative definite subspace. And B plus and minus. Well, that's the dimension of H plus and minus of x. So sitting here is not much. That's it. That's B plus of x minus E. So that's okay. Great. So and just I know for later, the other characteristic of x is going to be rewrite it in terms of B plus and B minus, like so. Okay. Now, all right. So this is going to be an important part of the story, but the more subtle part is spin geometry. And Andras set this up very well. He noted that that there was this map from the unit quaternions SP1 times SP1 to the FL4, which send the P plus and P minus to the map that sends so I'm thinking of R4 as the quaternions, and it sends it to plus B minus R. Q plus and Q minus R unit quaternions. And this was a 2-to-1 map, and it gives you an explicit construction of the universal cover of SO4 spin form. And let's say, yeah. So spin structure that's a lift. So if I look at the orthogonal frame bundle of my Riemannian manifold, it's got an action of SO4 on it. And spin structure is a length of this uh, action so that fiber-wise over the base, this looks like the usual action of spin 4 of itself. Okay. And the I'll see a little more concretely what this means in a second. So yeah. Right, so a nice way to say this. So this is the 2-to-1 cover. So so this guy so this is determined by a class in the H1 of frame bundle with Z2 coefficients. Right, this is a double coverage using such a class. And that class has to have the property that on each, when I restrict it to each fiber, it's non-trivial. And if I look at the spectral sequence for this vibration, it's maps the A2 of the base, you see 2 coefficients, and it maps this diagram. So it's an element here, but this has a map. This has a map. I don't say it that way. And, the way I want to think about this is something. What does this spin structure give you? Well, spin structure gives you a particular 2 lead vector bundles. So bundles S plus and minus, which take spin structure and and I tensor over H with delta plus and minus. Those are the projection from spin form these 2 factors. And sections of here, sections of S plus and minus are called spinners. And what's particularly important, I think this is more the way topologists think about it, but what's important for us is that there's the Clifford algorithm. So the Clifford algebra in general, if I'm having a vector space with a quadratic form, then the inner product of the Clifford algebra of this pair is the tensor algebra modulo the ideal generated by V tensor V minus V of V times 1. So in dimension 4, R4 is the standard inner product. This the Clifford algebra. The Clifford algebra of R4 with the standard inner product is isomorphic to two copies of the quaternion algebra, plus and minus. And concretely, we can think about it this way: the action, say it. So if I again have my orthogonal basis, then these guys are supposed to give me quaternions, and they give me well, two copies. So this guy maps to
So what's the real dimension of things?
Sorry, I should have said this one. Sorry, not quite enough sleep. Fuzzy brain. So Clifford algebra, one thing to notice is that as a vector space, the Clifford algebra of V is isomorphic to just the exterior algebra of V. So that tells you what its dimension is. You see that because if this is an inhomogeneous ideal, but it's filtered. So we can take the associated graded. I mean, the Clifford algebra is a filtered algebra. And if you take the associated graded, it forgets about this. And that's the relation that gives to the exterior algebra. So, okay, so so one thing that's important to notice is that each of these guys is it's a skew symmetric matrix with the property that it squares to -1. Right? So let's call this, as we will, this map is called C, and you know that C squared is so C adjoint of V is minus C of V, and C of V is minus C of V. Okay. So great.
Okay, so
Yeah.
E1, E2, E3, E4, you see them as what the so this
This is it. And well, I'm going to think of them strictly speaking are for dual. I want an action of
if you want me to
so
start with the
so I want to explain the identification of the Clifford algebra with 2x2 quaternion matrices.
yes.
Right. So what I need to do is define a map on V, which is R4, to
But only have the tension vector the TV.
sorry. Let's test it out.
The sense that
Sorry. Yeah. Unfortunately,
is the plus sign.
sorry, plus sign. Thanks. Yeah. Absolutely, it's a plus. Unless I'm working with negative definite matrices. I mean, intersection. Anyway, okay, so So the upshot is that so these guys are so the Clifford algebra of R4 is 2 by 2 quaternion matrices. This ideal is of even degree for the tensor algebra. So the Clifford algebra in general, it decomposes into an even part, and the even part of the Clifford algebra of R4 is isomorphic to 2 copies of the quaternion algebra, and what these bundles S, the bundles S plus and S minus, they're a reflection of this. So the spin group actually sits inside the Clifford algebra, and the projection of the spin group, the projection, the spin group then acts on each of these guys, giving me delta plus and delta minus. And in particular, so the important takeaway now is that there is global action of the Clifford algebra of the, I want to take the cotangent on S plus S minus, S plus S minus. This action, you should think of this as a kind of Z2 graded picture. This is a Z2 graded algebra. This is a Z2 graded vector space, and so this is a map of Z2 graded things. In particular, I'm going to call this map C, and in particular C of a one form, and if that's an S plus, and if that's a one form on X, then that's in S minus. Yeah.
When you write the tensor algebra just R4, you're assuming that the standard
Standard inequality.
Yeah.
Positive, standard positive definite inequality. So, I mean, from this description, it's clear that these vectors switch them into components. Okay. So, great. Now, all right, and all right, there's an important generalization. I'm sorry, I want to say, yeah. So the instruction. The existence of this student structure is that people with the class of tangent bundle, if W2 of X I will denote as W2 of X, if that's 0, then the set of spin C structures spin structures. Is a torsor for H1 of X with Z2 coefficients. And concretely, you can see that from this picture. So one thing to notice that this being a matrix algebra, it has a unique irreducible representation coming from its action on quaternions, two combinations of quaternions. This action is very rigid, but what do I want to say? Yeah, but how do I think of, suppose I have a spin structure. So sorry, I should say a spin structure is equivalent to having this data. If I have a pair of bundles with an action of the Clifford algebra, that's the same thing as having a spin structure. Okay, and it's kind of better to think about it this way for our purposes. So this is one, two. All right. With that said, I can make this a little more concrete. So how is it for sort of, this is the same thing as isoclasses of real line bundles. Okay, and if I have S plus and S minus with this action, I can replace it by S plus S minus tensor real line bundle. But viewing this action, I'm going to drive you crazy. Viewing this action of a map from the Clifford algebra, the maps between here and here, when I tensor with the same thing, that's canonically isomorphic. So, all right. Now, what we're going to need is not just spin structures. Well, one thing, spin structures are going to play an important role, and it's important to realize that there's this quaternionic nature in a spin structure. But there's a natural generalization extension of this idea, which is spin C structure. So spin C form is spin form times U1 divided by plus or minus 1. There's the canonical plus or minus 1 means 1, 1, that's 1, and minus 1. So the pre-image of the identity in SF4, that's acting here, and U1 is just U1. What's the deal with this? Well, the spin form C is the symmetries symmetry group of not the Clifford algebra of form, but it's the Clifford algebra tensor with complex numbers. The Clifford algebra tensor with the complex numbers is 4x4 complex matrices tensor that turned into itself 2x2 complex matrices. Again, there's a decomposition into even and odd, which each of these are the even part is 2x2 two copies of 2 by 2 complex matrices, the tensoring you'll see the 2 copies of H over there. And so if I have the spin C structure is then in these terms, it's the same gadget, except that how many times can I do it? It's the same gadget, except that I tensor this with C. So C, the code management bundle, the tensor series, a pair of vector bundles. That's in slides. That's tensor over R over there. Okay. And now, so spin 4C has a bunch of interesting maps. It has, first of all, map B1, which we call the determinant. It has a map to SO4, which forgets about the U1 factor. And and we're going to call these, well, they're really Fraktur S's, but we'll see. So this determinant bundle gives you a preferred line bundle. Corresponding to the determinant homomorphism. So what about the existence of a spacey structure? So the existence is a little more interesting. So you notice that there's this determinant homomorphism. That's the U1 over plus or minus 1, but that's U1 if you here. What do I say? Yeah, so so there's an interest. So if I have a spin C structure within this CS, there's a preferred cohomology class, which is C1 of this determinant line bundle, which is even, we'll just call that C1 of S. And integer cohomology, and some facts about this is that C1 of S is, if I reduce it mod 2, it's the second Stiefel-Whitney class of the tangent bundle. And existence of a spin C structure. And so existence is equivalent to, well, W2 of X, admitting an integer limit, which is equivalent to the vanishing of the integral third Stiefel-Whitney class. And it's a theorem, I think, probably due to Whitney, that actually for individual parameters with four manifolds. I just forget that's zero. I can't write SW class because SW is going to be Seiberg-Witten. But you notice in particular, if the manifold has no, if it's simply connected, then they certainly have one. That's up. And so we have this first Fredholm class, we have existence, and what about uniqueness? So in C structures, X for H2 of X with integer coefficients, i.e. isoclasses. Complex line bundles. And notice I can play the same trick to explain where that action comes from. So if I have beta X is a C bundle, then I can replace S plus S minus that S plus S minus tensor E, and then again this action I'm allowed to tensor both of these guys in bundle. That's fine. And it's important to think about how C1 behaves. So I'm going to denote this. So S goes to S tensor E, and C1 of S tensor E is equal to C1 of the original S plus twice C1 of E. The twice is related to the determinant of homomorphism. Squarely. And you notice that that's quite interesting. So, just to connect with what Andras was saying, remember there's a notion of odd and even, and in a simply connected case, that's determined exactly by W2. An integer vector, which so W2 for so W2 has this property that if I square a class and reduce it mod 2, it's W2 mod 2. So sort of W2 W2 vanishes, then the intersection form is even. Any C in relation to X Z, so that with this property, so just the alpha is C dot alpha mod 2. That's called characteristic. The mod 2 intersection form is a homomorphism, and it's if a kind of vector that realizes that over the integer is called characteristic. So in the language of quadratic forms, and what we learned from this is that the first Chern class that's in C structure is gives you a characteristic vector in the cohomology. So it's important then to realize that what the spin C, what the possible first Chern class of spin C structures are all possible characteristic vectors. Yeah.
Sorry, what does it say if W2X is on the bottom?
Sorry, where?
Right now.
Yeah.
Product.
Yeah. Yeah, and evaluated in the fundamental devices, it's not too. Okay, so, great. Okay. Now, that's been C structures and all that. Great, okay, and now, I think we can start to introduce the important players in the game. So the first yeah. We start to introduce some different geometry, so you can see connections. So I have these spin bundles, S plus and S minus, and so in the spin case, if I have a Riemannian manifold, then the tangent bundle or cotangent bundle, they have a canonical connection, Levi-Civita connection. Because this is a double cover, a connection on the Levi-Civita connection induces also a connection in the double cover. And so it induces a connection on the spin bundles. Now, things are a little more complicated for this, let's call it strike line in C case, but spin C4 maps to SO4 times the C1, looks like plus or minus 1 here by I and det. And so if I think globally, right, a spin structure in particular, spin C structure in particular gives me a circle bundle over the frame bundle. And if I want to specify a connection in that, it's not enough to use the Levi-Civita connection, I need a connection in the determinant bundle. But if I have a Levi-Civita connection and a connection in the determinant bundle, give me a spin C connection. So given Levi-Civita connection and a condition connection in L, S, we get permission connection, let's call it A in the L, we get a connection. Now with A, what does the connection do? It's going to take a section of S plus and minus and give you a section of S plus and minus tensor the cotangent bundle. Okay, great. Now, and an exercise is to see that spin C connections play well with the Clifford algebra. So if I take the covariant derivative of some form acting on a spinner, then I just get the Leibniz rule. So C is parallel. So each beta connection differentiating theta, then acting on phi plus C acting on the. So that's just the Levi-Civita connection, and here this guy. Okay, so that's if it's a spin C connection, it has this property that's characterizes what spin C connection is. All right. Now, now we can introduce the Dirac operator. Okay, what's the Dirac operator? Well, Clifford multiplication gives us a map. In particular, I just restricted to one forms. It gives us a map from S plus plus S. The potential bundle depends for S plus S minus back to S plus S minus. Okay, so that's. So remember, this was acting on all forms, but this is just the restriction to one forms. And well, we stare at this for a moment. And then we look up there and we notice there's an interesting thing to do. We can compose. So what we can do is go from infinity minus we have covariant derivative, it's the infinity of x. Tensor potential bundle. Potential bundle tensor s plus s minus. And then I can do pointwise Clifford multiplication. Back to sections of s plus s minus. And this composite is the amazing and wonderful Dirac operator. Okay, yes. And it is so. So, in few words, so the Dirac operator obviously was originally defined by Dirac, right? And he defined it because he was trying to study the properties of the electron. He decided that electrons were special kinds of things. They were spin 1/2 particles. That's what the 1/2 was thinking about the representation theory of SON, but there are these kind of fake representations, which are really representations of spin. Anyway, and then it was rediscovered in the 60s by He and Singer when they wanted to prove the index theorem. And the Dirac operator, or if you like, maybe just understanding this connection to the Clifford algebra and Clifford multiplication, you can think of this as saying that the okay, so the existence of a spin structure is in algebraic topology terms is the existence of a KO orientation for X. The existence of a spin C structure is the existence of a K orientation, if that's the language you speak. If it's not, it's just this. Anyway, but you know, it sort of had the Dirac operator is somehow a very fundamental thing, obviously in physics, but also in mathematics. It's in some sense the thing that generates every operator there is, in some sense. Okay, so very important operator. And this is, I'll explain this a little bit more, but this is an example of, should say, this, I'm going to call this B tilde because it's B tilde, but it maps sums of these guys, the sums of these guys, but because the Clifford multiplication of one forms is off diagonal, it actually decomposes as a map. From S plus to S minus, that's what I'm going to call BA, and then its adjoint, a map from S minus to S plus. By the way, remember the action of the one forms was by skew symmetric matrices, and you might wonder, well, why is it the adjoint here as opposed to minus the adjoint? And the reason for that is because this guy's differentiating. And the adjoint of differentiation changes the sign as well. So this guy is really the adjoint. Anyway, now this guy has no. So this is we tell the A are the operators. Because the Fredholm. They have 5-dimensional kernel and co-kernel, so there's an index. And the index that we told them that's 0, but there's an interesting index problem, which is being the index of dA. And maybe I will end with that. A couple of interesting things that happen in many. So so with index if we have for just a spin Dirac. Sorry, I could have constructed the Dirac operator if I just had a spin structure. Everything looks the same except I don't need the A. Right? So for the spin Dirac operator, which I was going to call it, maybe I'll call piece, assuming there's a spin structure, then its index is minus 1/8 with signature. Okay, now that's really interesting when you think about it. It's saying signature is divisible by 8. And remember, if it's spin, then W2 is 0. So that means the intersection form is even. And you say, well, okay, great. We saw from Handrash's lecture that actually the signature was 0.16. That was roughly 6. But this is the index over C. And it's gone now, but the spin Dirac operators actually could turn the onity action. So that means that actually the index is the complex index is even. Right. So this implies the case theorem. For the spin C case, the index against C of e to the A is what? Well, there's still this thing, but there's also C1 squared. There's also C1, it's minus the signature plus C1 squared of the spin C structure divided by 8. And you notice this is interesting too. That's telling you this is divisible by 8. This is an integer, but this is divisible by 8. And well, that is a theorem about quadratic forms. The square of a characteristic vector is always divisible by 8. That's a generalization of the fact that for any for any even form, the signature has to be divisible by 8. For any quadratic form, in fact, the proof is you prove it for odd forms, odd indefinite forms, very easy. And then notice that stay longer. You write something, and then you prove this. So But this is an analytic proof, this is an. Okay, I think I'm supposed to stop now. Thank you.